Welcome to The Explainer. Today we're diving deep into one of the most incredible tools in modern medicine's arsenal against cancer, the medical linear accelerator, or as it's more commonly known, the LINAC.
You know, it all comes down to this one huge challenge. It's the question that has been at the heart of radiation therapy for more than a century. The mission is, and always has been, simple to say, but incredibly hard to do. Hit the cancer hard and leave the healthy parts of the body alone.
All right, let's get into it. We're going to start with a quick history lesson, going from the early days of cobalt to the LINAC. Then we'll peek inside the machine itself. After that, we'll see how that raw power is sculpted with amazing precision. And finally, we'll talk about the promise of quality assurance that makes it all safe.
So to really get why the modern LINAC is such a big deal, you kind of have to understand where we came from. The evolution from what was basically a blunt instrument into a finely tuned surgical tool, well, it's a pretty amazing story.
The 1950s, man, that was a huge decade for this field. Two different technologies came onto the scene at almost the exact same time. On one hand, you had the Cobalt-60 unit, a real workhorse that used a radioactive source. On the other, you had the LINAC, this new kid on the block that was all electric. And while they were both game changers at the time, one of them was about to completely rewrite the rules of cancer treatment.
So what's the real difference here? Well, think of it like this. A Cobalt-60 unit is like a really powerful, reliable candle. It's always on, it's always producing one kind of light, and you can't turn it off. The LINAC, though, that's like a high-end digital projector. You can switch it on and off in an instant, and you can change the image, the energy, the shape, the intensity on demand. That level of control, that was everything.
Okay, so how does this beast actually work? How do you take regular old electricity from a wall socket and turn it into a high-energy beam of X-rays that can target a tumor buried deep inside a patient? It's a heck of a journey, and it all happens at nearly the speed of light.
The magic behind how a LINAC makes X-rays all boils down to this really cool physics concept called Bremsstrahlung. That's a German word that literally means braking radiation. Just imagine a speeding race car slamming on its brakes. All that massive forward energy has to go somewhere. In a LINAC, when an electron does that, that energy gets converted into a powerful burst of X-ray.
And this whole chain reaction happens in less than a microsecond. First, an electron gun, kind of like the one in an old tube TV, fires off a stream of electrons. Then, powerful microwaves kick in and accelerate those electrons down a special tube, pushing them to almost the speed of light. They slam into a hard tungsten target, and bam! That's the braking, the Bremsstrahlung, that creates a cone of X-rays. But we're not done. That raw beam gets shaped by a flattening filter to make it uniform, and then heavy metal jaws give it a basic rectangular shape.
Okay, creating a perfectly uniform rectangular beam of radiation is already an incredible piece of engineering. But here's the catch. Tumors aren't square. They're never perfect rectangles. They're messy, irregular, 3D shapes.
Right. This is where the machine goes from being just powerful to being surgically precise. To really do the job right, we need to be able to sculpt that beam of radiation, to wrap it perfectly around the tumor and avoid hitting the healthy stuff that's right next door.
And the answer is just brilliant. It's called the multi-leaf collimator, or MLC. The best way to think about it is like an automated high-speed stencil. It's made of dozens of pairs of thin, computer-controlled tungsten leaves, or fingers. Each one can move in and out on its own, and together they can create a custom-shaped opening that perfectly matches the tumor's outline from any angle.
Now, if you take that a step further, you get to something called intensity-modulated radiation therapy, or IMRT. This is where it gets really wild. With IMRT, those MLC leaves don't just set one shape and stop. They're actually moving while the beam is on. They're literally painting the radiation dose across the tumor, layer by layer. This means you can blast the densest part of the tumor with a high dose while delivering a much lower dose to the edges that are near a critical organ.
But you know, not every adjustment needs to be that high-tech. Sometimes a simpler tool is just the ticket. For example, if the beam is hitting the body at an angle, the dose can get skewed. To fix that, a simple physical wedge. Yep. A wedge-shaped piece of metal is slid into the beam's path. It's thicker on one end, so it evens out the dose across the target. Simple, but incredibly effective.
So we've got this incredibly powerful beam and these amazing sculpting tools.
But with all those moving parts, all those calculations happening in a split second, how can we be 100% sure that every single treatment is delivered perfectly?
The answer isn't, "we hope so." The answer is a rigorous, absolutely non-negotiable system of checks and balances. This is the domain of the medical physicist, and it's called the Quality Assurance Promise.
It starts every single morning, before the first patient even walks in. A medical physicist runs through a whole battery of daily checks. Is the radiation output exactly what it should be? Are the lasers that guide the positioning accurate down to a couple of millimeters? Are the safety systems, like the door lock and the cameras, working perfectly?
Then, once a month, they do an even deeper dive. The physics team gets in there and measures the actual profile of the radiation beam, its shape, its energy, its flatness. They make sure the light field you can see lines up perfectly with the invisible radiation field. They check every angle, every position indicator, making sure the accuracy is within a single degree or a millimeter. So this is the really critical question. What happens if, say, a monthly check finds the beam profile is just a tiny bit off? The answer is simple and absolute. Treatment stops. The machine is immediately taken out of clinical service. A physicist then has to hunt down the problem. Maybe it's adjusting the tiny steering coils that guide the electrons or tweaking the position of the flattening filter. No patients are treated on that machine until it is fixed, recalibrated, and passes every single check with flying colors.
And this quote just nails it. The entire point of this relentless QA process is to make one simple promise, that the dose the doctor prescribed is the exact dose the patient receives. It's the foundation of trust that the entire field is built on.
All right, we've gone through a ton, from the history of the LINAC to the nitty-gritty of its daily checks. So let's just quickly boil it all down to the main takeaways from this explainer.
So, in the end, the LINAC isn't just a machine. It's a whole system. It's about combining immense power with incredible precision, and then wrapping it all in an unbreakable blanket of quality control to make treatment as safe and effective as humanly possible.
And this number right here, this shows you what it's all for. In modern radiotherapy, a key goal is to make sure that at least 95% of the tumor gets hit with the full prescribed dose of radiation. To be able to achieve that, to hit a complex three-dimensional target that consistently, well, that's only possible because of the LINAC's precision.
And you can see the results of that precision right here. All this advanced tech, like IMRT, means the total dose of radiation hitting healthy tissues is drastically lower than it was with older methods. But the quest for perfection never stops, which is why the field is always pushing toward things like proton therapy to spare even more healthy tissue.
You know, this whole journey, from just flooding an area with radiation, to sculpting it, to guiding it with live images, it's a story about the relentless pursuit of precision. And that leaves us with one final, really exciting question. As our ability to see and track a tumor in real time gets even better, what's the next revolutionary breakthrough going to be?